Hello everyone, today we are going to go through a new paper called LongVILA Scaling Long Context Visual Language Models for Long Videos. The authors discuss their solution to scaling up visual language models for longer video content. They call this model LongVILA and break down its components into three categories: systems, model training, and dataset development. They discuss the improvements made to their models with respect to scaling the input length and processing longer videos, and they state that they are able to extend the feasible frame number from 8 to 1024, improving performance on a long video captioning task by 60%. This was achieved through a combination of dataset construction and multi-stage training. The results are demonstrated to be robust across longer videos up to 1,400 frames. The paper also discussed how foundation models are being developed to tackle various tasks through a unified approach, leading to the emergence of artificial general intelligence. It highlights two key areas of focus: multimodality and long context capabilities. Multimodality enables the model to accept input from different sources, allowing for more versatile interactions like chatbots or robots. This development is seen to be a crucial step towards achieving AGI, where a single model can handle multiple tasks and adapt to new situations. The authors also discuss how their proposed model can handle both visual and language inputs while processing long videos. They mentioned the importance of supporting long context for foundation models like theirs, and they cite some examples such as processing hour-long videos, long documents, and large code bases. This highlights the potential of LongVILA to contribute towards achieving AGI by being able to tackle complex tasks involving extensive amounts of data. The authors also point out that there's a lack of research on multimodal models with long context, and this indicates a gap in the current approaches. The authors also say about the limitation of the current approaches for scaling up visual language models for long videos, and they highlighted two main issues. First, the use of discrete tokens in the vision parts, which hinders the image-video understanding, despite simplifying the system design. And secondly, the limitation of extending context windows through training and inference methods proposed by previous works, such as ring attention and LongVIA. The authors emphasize the need of full-stack design for long multimodal language models compared to traditional machine learning algorithms. The authors note that there are more challenges when scaling up multimodal language models like LongVILA compared to text-only models. They highlight two main issues that require component code design. Firstly, these models have different architectures than text-only models, which requires a different distributed training strategy to handle their larger size. Secondly, they mention that it requires more data engineering efforts. They discuss how scaling a visual language model with long context and multimodality abilities requires a full-stack design to match the increased model size and context length. The paper also highlights the importance of collecting large amounts of high-quality visual language data and implementing an efficient infrastructure to support the training of the long-context visual language models. They also address the issue of high memory usage in their model during inference by implementing an inference mode of their own MMSP architecture. They also mentioned that they have implemented their MMSP system to be compatible with Hugging Face, which makes it much more easier to use. And they also discuss the model's ability to handle long videos and its performance on video captioning and question and answering tasks. They mentioned that they have developed a method to scale up a short context visual language model and a vision encoder into a long context model. And this new model achieves better results than current state-of-the-art models on these tasks. The authors discussed the limitations of decoder-only visual language models, and they say that this is due to the fact that they lack the efficiency provided by encoder-decoder models due to their inability to make use of multimodal projectors, which reduce the number of tokens processed by the decoder. This makes them computationally costly compared to encoder-decoder models. And they also mention an issue where long context visual language models tend to struggle with reducing the number of tokens per image or frame due to memory limitations. And there are different ways to distribute the computation of the attention module across devices by dealing with large sequences in text-based models. They mention two specific approaches: ring-style systems, like those presented by Lee and Liu, which uses point-to-point communication to collectively compute the attention module, and deep-speed Ulysses, which changes the sharding dimension to perform all-to-all communication. Right? And not only that, they introduced a new approach that's specifically tailored for visual language models, incorporating both all-to-all and point and P2P primitives to optimize performance. They discussed the challenges that they face when scaling up their visual language model to handle longer videos, and they also mentioned that training with such long videos tends to increase the memory usage, and not a single GPU can handle that. And not only that, but the current solutions like fully sharding data parallelism, FSDP, is not sufficient to address their issue. So, and not just that, but the current state-of-the-art models are not capable with long context requirements of their visual language models because they're only designed to deal with text-only LLMs in mind, and it lacks the efficiency and scalability to process the modality heterogeneity of visual data. The authors explain how scaling up their model, LongVILA, to process longer videos is necessary due to its applications in tasks such as video captioning and video retrieval. To do this, they implement several strategies, including distributing placeholder tokens, such as the image placeholder across different GPUs, and employing network heterogeneity. This is because when processing videos, the visual text modalities require different amounts of computation and therefore need to be balanced across different GPUs. It also talks about how previous works ignores such heterogeneity of networks when applying parallelism to multiple nodes and utilize point-to-point communication. This results in higher communication costs, which may not be fully overlapped with computations. The authors also highlight the limitations of their previous study, including being unable to hide the communication overhead and slowing down the computation kernel. So they propose using all-to-all primitives to reduce communication volume, but they also note that this approach has a few drawbacks, such as binding parallelization to the attention height dimension rather than the sequence dimension. This limitation means that simply using deep speed may not be sufficient to scale beyond the number of attention heads, as seen in the case of Llama 3 8 billion parameter model with 8 attention hits. The authors discuss issues with current models' ability to handle long video inputs, and they say that the maximum achievable sequence parallelism degree under the current approaches is only limited to 32, and this is not enough to process very long videos such as an entire movie. The authors propose a two-stage sharding approach to optimize computation workload for image encoding and language modeling stages. In the first stage, images are distributed across devices to balance the load during the encoding stage. Then, in the second stage, global vision and text inputs are gathered for token-level sharding. Additionally, the authors extended sequences with dummy tokens to maintain consistency when using ring-based attention. The authors also implemented a balanced sharding strategy to distribute context to each rank from both ends of the long video data, which ensures that each rank has an equal amount of work to do, right? And this entire approach minimizes the overhead while achieving scalable computation. Additionally, they utilize a 2D attention mechanism within the LM backbone, which enables efficient sequence parallelism. The authors proposed this approach called 2DSP that combines 1DSP along with sequence and attention dimensions to achieve higher efficiency in processing large-scale language models. This 2DSP approach converts the original 1DSP into a 2D mesh with Ring P2P and Ulysses A2A process groups. An example is given in the paper where an 8-degree sequence parallelism is achieved by constructing a 4x2 communication mesh using 2DSP, distributing the query key value tensors according to the head dimension. And it also explains how they balance the computation among the nodes and how their method compares with other methods like ring attention in terms of computation distribution. They use a 2D attention mechanism with ring parallel degree of 2 and a head parallel degree of 2 to achieve load balance. They use an all-to-all approach operation to distribute the KV tensors based on the head dimension across devices to ensure efficient and balanced computation. The authors also incorporated a workload balance strategy within the ring-based process group, and they say that the current inference system built on Hugging Face is limited due to their inability to handle long sequence lengths. And they also say that the pipe parallelism, which shatters the model, scatters the model across different GPUs, is not efficient because it only activates one GPU at a time and struggles with long sequences. So this suggests that there may be a need for more scalable inference methods to handle longer videos. And they propose using sequence parallelism to scaling up long context visual language models for long videos, right? So this approach enables faster inference compared to the ones used by Hugging Face. And this sequence parallelism enables multiple devices to jointly compute during inference to accelerate the process by the number of devices used, right? And the model is scalable because the memory is evenly distributed across different machines, and this allows it to handle longer sequences by simply adding more machines. So, and I also mentioned that this scaling is important because it doesn't require any retraining or redistribution of the weights when you add in more machine. And not only that, but they also propose a 4-stage process for training their model, starting from the first stage where they freeze all parameters except the multimodal projector. This initial stage aims to bridge the gap between language models and visual encoders. In the second stage, the authors freeze the visual encoder while training the language model and multimodal projector together. They continue this process with an extended pre-training approach using text-only datasets to increase the context length of the language model. And finally, they perform a multitask supervised fine-tuning to improve the model's instruction following capabilities. Right. And now, the training process of the model consists of 3 stages. Firstly, it uses the multimodal projection to align the visual and language representations, and then it conducts a large pre-training to develop the model's ability to handle different modalities. And lastly, it performs short supervised fine-tuning using a small dataset with labels that allows the model to specialize in certain tasks. They also extended the context extension stage from their previous work by incorporating more training data and using different methods to extend the context for the LMs. And they progressively increased the context length of their model using a training schedule to reach a final context length of around 200,000 and 60,000. They also implement sequence parallelism and low-rank adaptation techniques for better efficient training and fine-tuning. And not only do they perform the training, but they also created a dataset consisting of 15,000 videos with 10 minutes in each to train their model. So the dataset is built using a shoot-to-story dataset, which originally contains short videos. And the model had 2 tasks to perform on these videos. Firstly, they have to generate captions and they have to answer the questions. The authors used the LongVILA 1.5 model to annotate short video clips and use an LLM to generate question and answer pairs based on those annotations. They do this for long videos segmented into smaller clips. The authors describe a new dataset called Video Genome 2.0. It's a dataset that tries to capture the diverse aspects of long videos. They break down the types of questions that can be asked about these videos into many different categories, such as spatial, attribute, action, object, OCR, synopsis, and temporal. This dataset can help advance the understanding of long video formats by providing a wide range of examples, right? And after that, they move on to evaluating their system from 2 different angles: the system's performance and the model's performance. They start with reporting their training and inference results to ensure the efficiency and scalability of their system. Finally, they present the evaluation results of captioning and instruction following. This passage talks about the training and inference system of their long context visual language model, and they implement it using Hugging Face, making it easier to use. So they obviously tested its performance against another system called Zigzag Ring Attention, optimizing loading and GPU usage, and found that their approach was more efficient. So they use FSDB, fair scale data parallel, to optimize memory usage and compare it to other methods like zero tree. And they also compare their model to Megatron, which has expert design optimizations. And they also tested out different parallelization strategies, including context parallelism and tensor parallelism within a node or across many nodes. And they also tested their long context vision language model architecture on a large-scale dataset across multiple A100 GPUs, right? And they use a batch size of 1 and a model size of 8 billion parameters. The authors also provide an ablation study of the visual encoder, which you can take a look in the paper, which they omit from the baseline Megatron setup due to its relative small size compared to the language model. And they also talk about the results from the experiments that they conducted, and they show that LongVILA model has a better throughput than other models such as zigzag ring attention and deep speed. And they also compared their model to an optimized version of another approach called ring-style sequence parallelism, which is implemented by Megatron. And they found that their model outperforms that same approach by a larger margin, right? And they use a hybrid strategy combining Megatron LM and LongVILA to improve their efficiency. And by doing that, they get a speed up of 1.1 to 1.4 times compared to the pure LongVILA implementation. However, it is important to know that the Megatron LM system has a few limitations, such as supporting lower maximum sequence length, right? So not just that, the authors also tested their model with a bigger cluster size and found that vanilla data parallelism fails to scale for longer videos due to out-of-memory errors. They also compared their model against other models like deep speed and zigzag ring attention, and they also found that their model can handle longer sequences while being scalable. Their new long context visual language model is used to train a system that combines scalability of an existing model with the high throughput of another model. And they found that this kind of hybrid, this kind of approach allowed them to achieve faster speeds and support longer contexts than existing models. In addition, they were able to use multiple GPUs at the same time to perform inference over a competing implementation. The authors also discuss how their model performs when dealing with long videos compared to other models like Hugging Face. And they say that their model can handle much longer sequences, and they also point out an issue with how Hugging Face is unable to handle lots of memory, and this can be a huge bottleneck. So in essence, the results show that their approach outperforms existing methods by reducing the time it takes to process longer sequences. Additionally, they also provide pretty strong evidence of the effectiveness of their approach by demonstrating its ability to handle longer videos, up to 2 hours, and accurately capture relevant information within those videos. Anyway, I hope this gives you a good overview of what the paper is about. Do check out the paper, make sure to like and subscribe, and I will catch you all in the next video.